In this presentation, we will focus on the idea of cross-curricular skills between mathematics and science, with a particular focus on problem-solving and cognitive processes. It centres on the importance of learning for understanding, regarded as a key feature in cross-curricular teaching and learning, in the literature used within this presentation. It also captures the constraints in adopting a cross-curricular approach within the classroom environment. Hayes talks about the integration of knowledge as a feature to cross-curricular approaches, pointing out that it's a way to support the transfer of skills and learning from one situation to another. So in other words, being able to apply previous knowledge, skills and learning to one situation to another. For the sake of this argument, let us assume that this situation is a problem. We can then assume that the ability to solve problems demand transferable skills. Haylock and Cockburn add emphasis on this when they ask us to understand mathematics as the growth of understanding in the building up of cognitive connections. In short, this means being able to make links between one situation or one problem to another. A theme falling from problem solving in both science and mathematics are terms such as inquiry and investigation. Haylock and Cockburn claim that an inquiry or investigation provides a context of thinking more creatively in mathematics. Firstly, it is clear that they view these terms on the same leaf, and secondly, they connect this word creativity into the means of investigating the inquiry, which we will look at in more detail later. Newton states that scientists put ideas to the test, which she says is a key tool for scientific investigation. Putting these ideas together, this tells us that investigating or inquiring is the process of connecting learning and understanding together, and then drawing to a conclusion, or maybe even a hypothesis. The question now is, how do we place knowledge together in the classroom environment? Think back to when you were at school sitting in a science lesson, knowing that at some point you would have to get out of your seat and do something. For some of us, this can be quite scary and out of our comfort zone. Hayes summarises this when he talks about the effect of crossing subject boundaries to encourage pupils to undertake active inquiry, to show initiative and discuss and debate issues. In other words, having the opportunity to think for themselves, finding out for themselves and making sense of what they've learnt. Within science, problem solving as an approach is useful because it involves processes of thinking and doing for some specific purpose. In mathematics, it is a collection of ways of thinking and reasoning, ways of organising and internalising the information we receive. In both perspectives, the common theme is thinking, and the connections that are made when this process is taking place, which begins to answer the question of how knowledge is placed together. Let us now come back to Haylock and Cockburn's use of the word creatively. The National Advisory Committee on Creative and Cultural Education linked the fostering of pupil creativity with the development of culture, in that original ideas and action are developed in a shifting cultural context. Putting this into perspective, this would mean being able to respond to what you learnt and how you can apply the knowledge in everyday situations. Original ideas could be referring to the ability to make connections that someone might not automatically put together, or working through a problem in a way that hasn't been thought of before. By enabling pupils to visualise and practice the links made in science and mathematics, this can be the beginning of developing the skills involved in generating original cognitive processes. Sir Ken Robinson defines creativity as a process of original ideas that have value, with emphasis on the fact that it's a process and not an event. Therefore, this process needs to be developed over time through a range of teaching and learning techniques in the classroom practice. Zohar focuses on this notion of teaching and learning for understanding, drawing together one method of generating original thoughts and connecting pupils' cognitive processes. He recognises that connected knowledge is tightly related to understanding, and that it should have a prominent role in modern science and mathematics curricula. In order for pupils to reach the understanding stage, they need to acquire the skills to make sense of knowledge and information, and then apply this to a situation or a problem they are faced with. They also need to be able to make connections between information and between cross-curricular skills. In basic terms, this would mean being able to transfer certain skills that they have acquired in a science lesson in a mathematics lesson. Looking at the cross-curricular links between mathematics and science in national curriculum, there is a strong link concerning the ability for pupils to think for themselves and make choices. For mathematics, the national curriculum states that pupils should be taught to approach problems flexibly, including alternative approaches to overcome any difficulties. In comparison, for science, it states that they should start to make their own decisions about the most appropriate type of scientific inquiry they might need to use to answer questions. In order for pupils to make their decisions, they need to be exposed to a range of cognitive skills and interpreting information in differing situations, in between these two subjects. Consider if you were teaching a maths lesson on data handling. Pupils can use the skills they have acquired in a science lesson. First, they need to be able to interpret the data, then what they can do and how they can use the data, and perhaps what the data doesn't show them. Pupils can acquire and use the skills involved in this particular process in both science and mathematics, bringing us back to Zohar's use of the term connected knowledge. In order to carry out these tasks, they need to be able to apply these skills and interpret the information on a scientific level as well as a mathematical level. Continuing on the subject of data handling, because it interconnects between subjects, we can also look at the role of ICT within this. Let us consider the effects of using ICT, both as a subject in the national curriculum and as a resource for teaching and learning. How can we use ICT to connect knowledge and understanding within science and mathematics? Williams and Easingwood mention how pupils can often find themselves spending too much time producing graphs from recorded data, gathered through pencil and paper methods, without giving any extensive thought to understanding what this graph itself is showing. They then go on to find a solution to this, in that by using data logging, granted as an additional method and not an alternative to producing graphs, the time spent on the collection of data can now be spent on the interpretation and analysis of the resulting information. This then provides pupils with the opportunity to gain higher levels of scientific knowledge and understanding. In this case, it also gives pupils the chance to apply their mathematical skills, providing a direct link in understanding the use of the topic in real-life situations. On top of this, Newton offers that, in developing ICT skills, children are encouraged to develop logical thinking, problem-solving abilities, and information-finding capabilities, all valuable in science. This is similar to Williams and Easingwood's view in that data logging would allow pupils extra time to really make sense of the data and what it is showing, consequently developing their information-finding capabilities and problem-solving abilities. So what does this look like in the classroom? Carl Rogers saw the teacher's role as a facilitator, in that they should create supportive learning environments where pupils grow to love learning. Rogers says that the student develops her own program of learning, alone or in operation with others. So if pupils collaborated and carried out investigations, they would be taking control of their learning, allowing them the chance to make decisions. We have already clarified that this is the aspect of learning supported by Hayes, Newton, and more importantly, the national curriculum. Rogers' theory further argues that the focus is primarily on fostering the continuing process of learning, and the content itself falls into a secondary place, taking us back to the notion of learning for understanding, and knowing how to use knowledge and information in more than one situation. Barnes says that cross-curricular learning is difficult to assess because in opportunistic, multi- or interdisciplinary contexts, learning occurs on too many levels and in too many domains. Due to this, it can soon become demanding for teachers to track individual pupils' learning during lessons, and because of this, their long-term progress. Returning to Rogers' theory, where pupils can take control of their own learning, one can visualize the challenges in depicting whether lesson objectives have been met or not. Zohar shares a similar view to Barnes when he looks at two types of learning, rote learning and deep or meaningful learning. He claims that these types of learning differ in terms of their expected outcomes. The outcome of surface or rote learning is the ability to reproduce the knowledge that has been acquired. In other words, it is easier to see who has understood the goal of the lesson when you know what you are looking for. Likewise, if the path of learning is not certain, then there isn't a correct answer, which poses problems in respect to planning. It is almost impossible to prepare for something that has no definitive outcome. To summarise, in order for pupils to make sense of their thinking processes, we need to allow them the opportunity to make literal connections. One way to do this is to connect the subjects themselves together. By enabling pupils to make the connections themselves and direct their own path of learning, providing them the chance to develop their cognitive processes as well as their ability to understand the knowledge they are acquiring. So that means they can apply their knowledge in real cultural shifting situations. As mentioned earlier, cross-curricular teaching carries some challenges. Nevertheless, the outcome in pupils' learning and understanding outweighs these exact challenges.